Welcome to 10.2, Separation in Space. Before we get started, I just wanted to make sure that you remember we had a line separation postulate and we've had a plane separation postulate, and now we're going to be talking about the space separation postulate. So if you need to review how these are three separate disjointed sets, you might want to review the line and the plane separation postulates. But basically the space separation postulate says every plane separates a space into three disjoint sets, the plane and the two half spaces. Now this is a lot harder to draw, so hopefully you can follow along with the representations that are happening. So here is a space. We're going to call it space 1 and space 2, and the blue line in the middle we're going to say is a plane. So that blue line, that plane, goes infinitely in all directions, but it's flat. So it separates the two different spaces. So because it's flat and we don't want to draw it as a line, we're going to draw it kind of like this rectangle here, and we're going to call that the plane. So this is the figure 10.5 on page 420, but I just wanted to let you know we're drawing this at an angle so that you can see that it is not a line, and it does take up that paper thin space. Okay, so in a plane, two intersecting lines form four angles. In space, what do two intersecting planes form? Well, they do form angles as well, but they're called dihedral angles. A dihedral angle is the union of any line and two half planes that have the line as the common edge. So that line is like the vertices that we've been used to being a point. The vertices is now a line, or the edge of the dihedral angle is the common edge of the two half planes. A face of a dihedral angle is the union of the edge of the angle and one of the half planes. So remember, you have two half planes and then the edge, but the face does include the edge. So here is two half planes, and we also have an edge, and we also have lines included in the planes. So if LMN is a plane angle of the dihedral angle, okay, so look at LNM, that's just a regular angle that we've been doing, right? And it's called a plane angle. And then the NM is perpendicular to PQ, then NL is perpendicular to PQ, right? PQ is a line, a segment, right? The measure of the dihedral angle is the measure of the plane angle in this case. So the lines that are drawn, like the ray NL, goes infinitely along that plane, so the measure is going to be the same. The angle measure is going to be the same as the dihedral angle measure. So just like with regular plane angles, the interior does not include the pieces of the angle. So in a plane angle, we say the interior is not the ray or the vertices. Same with the dihedral angle. It's just the planes make it have an interior. Okay, so that's actually the entire lesson. I know that seems kind of crazy, but I do want you to look at figure 10.7 on page 421. they are naming the dihedral angles, and I didn't go over that. So if you're looking at the two planes that are intersecting one another there, you name it by a point on the plane, then the segment as the vertices, and then the other plane, and you put hyphens in there. So I really need you to look at that because I'm going to give you some practice problems naming the dihedral angles. And since I didn't show you a slide with that, it's really important that you look at page 421. So here's an example of naming the dihedral angle. So this is where I was going to talk about it. Now, remember, this WSQ summary needs to be submitted through email. And I hope you remember your set notation here.